This is section 9.3, separable equations. Our first objective is to solve initial value problems using separation of variables. When we're done, I'd like you to be able to explain why we only need to add c to the x side of the equation instead of to both. Before we get into the objective, we want to recall that a differential equation is any equation involving a derivative, and that when we find a particular solution to that differential equation by selecting one solution curve that passes through a given point, we have solved the initial value problem. With this lesson, we are going to connect how we found specific antiderivatives to a new concept that is called separation of variables. So first, let's read the algebraic steps for this separation of variables process. The first step is you separate variables so that all the y terms are together on one side of the equation and all the x terms are together on the other side. Now, the biggest error that people make in this particular step is they forget to keep both the dy and the dx on top. They should never ever be on the bottom of the fraction. The second step is you're going to integrate both sides and add c to the x side. Now, the reason we only need to add the c to just the x side is because adding it to both would enable us to move the c from the y side over to the x side and then combine those two c's to create a third c. Since that c is just a random constant and we have not plugged in the point to figure out what that constant is yet, we can do whatever we want to it and it's still just going to be a c. So let's say you've done steps 1 and 2. Once you do that, you'll be at a crossroads, and you're going to choose your path depending on the type of antiderivatives you have on both sides and how comfortable you are tracking changes to c through the process. You can always use either method, but sometimes one method will algebraically be more complex than the other. So deciding which path to use will come with practice, though a general rule of thumb is that you'll want to use path 2 whenever your antiderivatives involve logarithms. So let's do example 1, and with example 1 we're going to follow path 1 all the way through so that you can see how path 1 works. So remember that step 1 is to separate the y's and the x's, and if we look here we can see that there's only one y showing up. On the right side, everything is already involving x's. So we can move this dx over to the other side by multiplying by dx. Now in step 2, I'm going to integrate both sides. When I do that, I ask myself, what did I take the derivative of with respect to y that gave me a 1? And the answer is a y. On the other side, we'll ask, what did I take the derivative of with respect to x that gave me this? So the antiderivative of that would be 9x cubed over 3, or 3x cubed, minus 4x squared over 2, or 2x squared, plus 5x, plus a random constant. So now we've done step 1 and step 2, and we're going to choose path 1. Step 3 is to plug in the initial condition. So here I've got a y that is a 0 when x is a negative 1. So I plug in that point just like we did forever ago in chapter 4, and we solve for our c. So this is a negative 3, minus a 2 is a negative 5, minus a 5 is a negative 10. So if I move that to the other side so c is isolated, I've got c is now 10. Now we're going to replace c in the equation that we had in step 2. So I go back up to the equation that I had right before I plugged in my point. And now I will isolate y. Well, y is already isolated, and I don't need to repeat because I'm finding the function y whose derivative with respect to x gave me this. So I'm done. Example 2 now is a little more challenging because we have the second derivative. So in order to do this one, I'm going to rewrite that second derivative as the derivative of y prime with respect to x. Now if I separate my variables, I will have dy prime equals sine of x dx, and when I integrate both sides, I will ask, what did I take the derivative of with respect to y prime that gave me 1? And the answer would be y prime. On the other side, what did I take the derivative of with respect to x that gave me sine? That's going to be negative cosine of x plus a constant. Now, again, I'm going to stick with path 1, and I'm going to plug in the point that I know from y prime. That says when I plug a 0 in, I get a 0 out. So I got a 0 out when I plugged in a 0. Negative cosine of 0 is a negative 1. Move that to the other side. I isolate my c and get c equals 1. So now I know that y prime, or dy dx, is negative cosine of x plus a 1. If I now want to solve for the function whose second derivative was sine, then I need to separate again. So I'll have dy equals negative cosine of x plus 1 all times dx, and now I integrate both sides and answer the question posed by the integral symbol. What do I take the derivative of with respect to y that gives me a 1? The answer is a y. What did I take the derivative of with respect to x that gave me negative cosine x plus 1? Well, that's a negative sine x plus another constant. So I'm going to put a subscript of 1 on this first constant and a second subscript so that I know that they're different constants. In order to solve for c sub 2, I need to use a point that is on y. The point that I have on y is an output of negative 3 when the input is 0. Solving for c2 yields the answer negative 3, so I plug that back in and I get y equals negative sine of x plus x minus 3. I could double check that this was the correct answer by taking the derivative. That would give me negative cosine x plus 1, and then take the derivative again. That would give me positive sine, and we would get the second derivative gives me sine of x. I could also double check by testing the points. When I plug 0 into y prime, I should get 0, and I do. And when I plug 0 into y, I should get negative 3, and I do. Now, after watching example 1 and example 2, you're probably furrowing your brow and thinking, I've already known how to do this. We did this back in chapter 4, and nothing has really changed except we're now using this integral symbol and we're moving dx's over. So with example 3, we're going to actually see why this separation of variables is so critical. With example 3, we see that x's and y's are all mixed up, so separating them does not involve simply moving the dx to the other side. Separating in this case means that we actually need to move this log natural of y to the left, we need to move this y to the left, and we need to move the dx to the right. So if we do that, we will get a log natural of y over a y times a dy equals a negative x times a dx. If I now integrate both sides, hopefully you will see that this right side is pretty easy to answer the question posed by the symbol, because what we take the derivative of with respect to x that gives us a negative x is simply a negative x squared over 2 plus a constant. The left side, however, is a little more challenging. We don't see this on our green sheet of antiderivatives that we should know, so that means we're going to have to do a substitution method. We're going to look for a u whose derivative is in the integral, and we can see that the log natural of y, whose derivative is 1 over y, is actually in there. So we're going to have to remember our 5-5 substitution method process. So for those of you who have forgotten, we will let u equal ln of y. So then du dy is 1 over y, which means that dy, which is what we need to replace over here, is going to be y times du. So if I go put that into the integral, I'll have the integral of u over y times y du, and we see that the y's cancel. Now I'm ready to answer the question, what did I take the derivative of with respect to u that gave me u? And the answer to that is u squared over 2, or the log natural of y, quantity squared over 2. So putting that in over here as the antiderivative, I will get a log natural of y that has been squared over a 2. So now, here is where we are at the crossroads because we've separated our variables in step 1. We've integrated both sides and added c to the x side with step 2. And if we look here, our antiderivatives involve some logs. So rather than doing path 1, we're going to try path 2. And path 2 involves, instead of plugging in the initial condition right now, we're going to isolate the y. So to do that, I need to move the 2. So when I move the 2, I'm going to multiply both these things by 2. So that will give me a negative x squared plus 2 times this random constant. So I'm going to put a C1 so that I can track the changes. If I take a random constant and I double it, I'm just going to get another random constant that hasn't been nailed down yet. The next thing I'm going to do is I'm going to take the square root. And be careful, because when you take the square root, if you're the one that introduces the square root, you need to put plus or minus. Now notice that we cannot distribute square roots over addition, so we're left with it like this. The next thing we do is we both sides, make both of these exponents of e so that we can use inverse relationships to get y by itself. So I have e to the plus or minus square root of negative x squared plus some random constant. Now, we know that y has to be positive. Well, that doesn't really help us because exponentials to anything is always going to be positive. And we know y of 0 equals e to the second. So if I plug in a 0, I should get an e to the second. So now I've got the same base. That means my exponents had better equal each other. So 2 equals plus or minus the square root of some constant. Because 2 is a positive number, we're going to take the positive root, which means that 4 will equal c sub 2, and we go back to when we plugged in the point, which was right here, and we rewrite it with the c plugged in. We'll have y equals e to the square root of negative x squared plus 4. Now some people will put plus or minus here, and they would be wrong, because if you have a plus or minus here, then for any single input you'll get 2 outputs, which means that y would not be a function. So we have to choose the branch that passes through the point. And because the point had a positive 2 as its exponent, we're going to use the positive root as opposed to the negative one. So the nuance of this is that on the AP, they will often force you to select the negative branch, because a lot of people would stumble upon this correct answer simply because they forgot to put the plus or minus. So they will expect you to know to put that plus or minus on and then select the proper branch based on what kind of an output you have in your given point. With example 4 now, we want to find f of x if f prime equals 1 plus f squared. Now this is a little strange because we have f's instead of y's. So it will actually be easier to work with if you rewrite this as dy dx equals 1 plus y squared. Once we have this set up, then we can try and separate. Now I have multiple students who try to separate this incorrectly. They try to subtract the y squared to the other side, and that does not work because the y squared is attached to this dx. So the only way I can get this away from the dx is to divide. If I divide, I'll get dy over a 1 plus y squared, and now I'm ready to integrate both sides. On the right, what did I take the derivative of with respect to x that gave me a 1? The answer is an x plus a c. On the left, what did I take the derivative of with respect to y that gave me a 1 over a 1 plus y squared? Well, hopefully you recognize that as the tangent inverse of y. Again, we're at our crossroads. We can either plug the point in now, or we can isolate y and then plug in the point. And personally, on this one, since there is no log involved, I find it simpler to just plug in the point now. So if I plug in the point where the output is 0, when the input is 0, then I can see that C will end up equaling the angle whose tangent is 0, which is just 0. Therefore, tangent inverse of y, I go back to the equation where it was when I plugged in the point, and then I solve for y. In order to get y alone, I need to tangent both sides. To double check this, I could take the derivative and get dy dx equals secant squared of x, and we can remember from our trigonometry days that sine squared plus cosine squared equals 1, which means if I divide everything by cosine squared, I'm going to get sine squared over cosine squared, which is tangent squared, plus 1 equals secant squared. So this dy dx is the same as 1 plus tangent of x that has been squared. And what do you know? That's the same as 1 plus y squared. So we got y prime equals 1 plus y squared. And if I plug 0 in, I get a 0 out.